We need to talk about Riemann sums. We have seen two ways of approximating the area under a function using Riemann sums. We've used left Riemann sums and right Riemann sums. Well, there are two other types that you need to know, and this little talk is about those. Just to recap, let's have a quick look at a typical problem. This is a real life problem because this is me. Just over a week or so ago, I was running in the Gay race in the forest, and I ran 1 hour and sort of like 23 minutes. But between the time of 50 minutes and 56 minutes, my watch here tells me that at these times I was running at this speed. Now obviously my watch actually gives me in kilometers an hour, so I've converted it, because we're talking here in minutes, I converted it to meters per minute. So at time 50 minutes I was running at 185 meters per minute. I then got a bit faster. After 51 minutes I was running at this speed, at 52, at 53, and so on and so on. That's a real life example of me running, and I've made a graph of it. Now you might say, Mr. West, you've done something wrong there, and you're right, I have. This orange function here I've completely made up. All I actually know are these values, these red points given to me from this table. But okay, I've said this is a possible function which could pass through those 7 points, sorry. Well, what have we seen so far? We've said that one way to estimate the area that's under this function is by taking left Riemann sums, rectangles, and taking the left-hand side. Let's have a quick look. It means we're going to have this. These are our rectangles. There are 6 of them. The width of each rectangle is 1. That's quite nice to see. And so therefore, our left Riemann sum, our approximation for the area under this function, or of course any other function that I would like to draw through these. I'm assuming that, I suddenly didn't start running at like 470 meters per minute between here and here. I'm assuming there wasn't some strange weird thing happening here. So I can say that the left Riemann sum is going to be, well, it's 1 times 1, because all of these rectangles have got width 1, and it's going to be 1 times 185 plus 228 plus 233 plus 222 plus 240 plus 240. And when you work that out, you can get out your calculators, and it works out to be 1,348 meters was the approximation for the distance that I ran there. That, of course, corresponds to what? It corresponds to this area. As you can see, this function is increasing and decreasing, so some of these areas will be underestimates, some of them will be slight overestimates. I think though, if you look at this fairly carefully, this one here, this first value is so different from the others, I think we can probably say that that's going to be an underestimate of the distance that I ran. Well, the other thing that we've looked at has been right Riemann sums. So this time, instead of what we did before, we're now going to say, let's approximate these areas by taking the right-hand side. And again, some of these are going to be overestimates, some of them are going to be underestimates. This one is, in particular, is quite a big overestimate. This one is an overestimate, but this one is probably going to be an underestimate. What does that give us? The right Riemann sum is going to be, again, we've got the widths are still 1, So it's going to be 1 times, and now it's just 228 plus 233 plus 222 plus 240 plus 240 plus 233. And the final answer we get there is 1396. So we're going to assume that I kind of ran something between 1,348 metres and 1,396 metres in that time interval. Now, there are 2 other ways, I mentioned at the start of this, that you can approximate the area under a curve. And one of them is called the midpoint approximation. And what it does is this. It says, well, since the left Riemann sum gave us this area, and the right Riemann sum gave us this area, why don't we take the value of the function in the middle? Now, if I knew what this function was, you could say, okay, that approximation will probably be better than the left and the right. Unfortunately, I don't know that value. So in this particular table, if I want to talk about the midpoint values, I've got to change the width of my rectangles. I don't know the value of the speed when the time was 50.5. So what I'm going to do is this. I'm going to use this as the width of my rectangles. So now I'm going to look at this rectangle. And I'm going to take the midpoint value. So in other words, instead of talking about these 2 rectangles, I'm going to say, let's have this big rectangle, and let's say that the width of that big rectangle, the height of that big rectangle, is just going to be that. I'm going to take that as the height of this wider rectangle. Similarly, for this one, I'm going to take this as the height of this wider rectangle. Again, you can see that sometimes we're going to get over approximations, sometimes we're going to get under approximations. So for this rectangle, I'm going to take the height as 222. And finally here, I'm going to take this big rectangle, and I'm going to take the height of that rectangle to be 240. And so my midpoint approximation becomes this. Well, each of these rectangles has now got width 2. So I can say it's 2 times, and then I've just simply got to add up these heights. And we get 228 plus 222 plus 240. And when you work that out, you get an answer of 1,380 meters. Now the fourth idea is actually a very, very useful one. The midpoint approximation has its uses. It's pretty good when you've got lots of values. The fourth one is called the trapezium sum. Now, American friends are going to get very upset with me because they, of course, call it the trapezoidal sum. They can use either. I don't care. I'm still going to use trapezium sum, but trapezoidal is the one that you'll see, certainly in the exam. And the idea here is simply that instead of taking, we now just say, oh, hang on, forget all this rectangle nonsense. Let's do this. Let's take the area as, I better use a different colour pen here. Let's take this area. The area of the trapezium between these points. And as you can see, the difference now between the left Riemann sum and the right Riemann sum is a lot smaller when you start taking trapeziums as your areas. But you do need to know the formula for the area of trapezium. We've talked about this in class a few times. What is it? You have to turn your head around and look at them sort of this way or the other way, whichever one you want to do. These are the bases now. This is the height. Oh, well, that's good. The height of the trapezium is simply, or 1 or however long it is. So you can simply say that the area is 1/2 times the height times the sum of the two bases. Now, of course, the sum of the two bases are simply the value of the function between here and here. So this, well, the value of the function here and the value of the function here. And so we're back to taking these as our intervals, but we're going to be building trapeziums. And the formula, therefore, becomes this. It's quite long, this, so often you need a calculator to work this out. Here we go. It's going to be 1/2 times. Now, again, here, the height of my trapeziums are all the same. If they're different, you can't take out this next term of 1 as a common factor. You must be very, very, very careful when these things go from like 50 to 52 to 55 to 56 to 59. Please, 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 when you're looking at examples, be very careful on that part, that you can factorize these out like we've done in all of these examples, simply because the widths were the same. So what have we got? It's 1/2 times the height times, well, the first trapezium, the A plus B, the two parallel sides is simply 185 plus 228. So 185 plus 228. That's your first trapezium. Plus, what's the next one going to be? Well, it's 228 plus 233. The next one is going to be 233 plus 222. The next one is going to be, where have we got to? 222 plus 240. The next one is 240 plus 240. And the last one is 240 plus 233. And when you work all this out, the answer that you get, I'll tell you for free, is 1,372 meters. Now, I'm sure you're dying to know which of these is the best. Well, because this function's increasing and decreasing, there are some rules that we can talk about online for when a function is definitely only increasing or only decreasing, as to which of these is the best approximation, which is an over approximation, which is an under approximation. But this one, because it's much more complicated, because the value's going up and down and up and down, all I can do is say to you that actually the real value that was given on my watch was 1,000. I actually ran 1,370 meters in this time. So as you can see, our final approximation, in this case the trapezium sum, was actually very, very accurate. to what I ran on that day. There are plenty of questions for you to do in the multiple choice booklet, or you can find other questions. I can send you a worksheet with some problems on. Have a look at them and have a go at practicing midpoint and trapezium sums, please. Take care.